All right, so today we're going to take a look at NS2. We're going to keep working with some long division. Put today's date, color your header. This is a new lesson. We're going to take a look at how are numbers divided to make decimal numbers instead of remainders. So remember when you were in 5th grade and you did a long division problem and you had 1 left over, they would tell you to write remainder 1. Well, that'll work if you're, dividing up some candy, and it's okay that you have 1 left over because both you and your friend are going to get 17 pieces. Maybe set that 1 piece aside for your brother or something. But if you're trying to take a measurement for a project, so you have to cut 2x4s, or you have to take a ribbon to make some bows and you cut that in half, you're going to end up with this strange leftover amount. Well, that can be turned into a decimal so that you can have a precise measurement and you can get a precise amount. So let's say that we take the same 35, we're going to divide it by 2 again. 2 goes into 3 once. 2 times 1 is 2. Subtract, bring down the 5. 2 goes into 15 7 times, which is 14, and we get 1 left over. Now we're going to do something that we don't think of very often, because whenever we write a whole number like 35, we just write 35. But there's another way to write 35. So there's something that I like to call, and this isn't a technical math term, but it makes sense when you think about it. It's called the invisible decimal. And the invisible decimal is the decimal point all whole numbers have but we don't write. So for example, 10 is the same as 10 decimal 0, 10 and 0 tenths. And just like our 35 here, 35 is the same as 35 and 0 tenths. So we can take that decimal point and we can put it after the 35. We can also put an invisible decimal right above it after the 17, because this is 17 whole pieces of candy. There's 1 left over, but there's 17 whole. So we can put that invisible decimal right there because it really is there. It's just invisible. We don't write it. So it does belong there. Then there's something else that we can do. It's called annex zeros. When we annex zeros, we're putting a 0 in a place that does not and I'm using all uppercase for emphasis. You can do that when you're taking notes. If you want to emphasize something when you're reading it back to yourself, you can change whether or not you use uppercases, you underline, you change the color. You can do all kinds of things to make sure, and then that'll help it stick in your head when you're studying later. So annexing zeros means that you're putting a 0 in a place that does not change the value. So when I annex zeros, especially when I'm first learning how to use annexing zeros, I like to make them red, because then it reminds me that it's in there to help with the mathematics, but it's not changing the value. So when I annex a zero in this problem, it's going to be to the right of the decimal. I'm going to annex that zero right there. And sometimes I have to go back and take my long division box and make it longer, and that's okay. That is part of the process. So as I'm annexing that zero, I'm sitting here and I'm saying to myself, well, I've used the 3 and I've used the 5. Now that I've annexed that zero, I can bring that down, and now I'm making 10. So now I can ask myself, how many times does 2 go into 10? And 2 times 5 is 10. And we subtract that and we end up getting to 0. So now I have a precise measurement. So if I'm cutting my ribbon, or I'm cutting a 2x4, or even if I'm cutting up some candy, I know that 0.5 or 5/10 is the same as half. It's half of the candy bar, or half of an inch if this is inches, half of a centimeter if these are centimeters, whatever the units are. So there's another term that I want to talk about. When we finally divided this out and we ended up with a complete number because it came to 0, that is called a terminating decimal. And it sounds pretty dramatic, but it really just means terminate, means to end. So a terminating decimal simply means you can divide to 0 and ends. So that's what happened there. We got to 0, it ended. We didn't have to annex any more zeros. It finally stopped. There was nothing else for us to do. So that is called a terminating decimal. And there's one more term that I want to talk about because you will run across this. I'm certain of it. And I'm going to do an example where we use a number that doesn't terminate. It doesn't come to 0. And that's called a repeating decimal. So let's take a look at, let's do 33. Yeah, let's try 31 divided by 3. I'm going to go right here. Three goes into 3 one time. 3 times 1 is 3. Subtract, and I get 0. I still have a 1 in this number, so I'm going to bring that down. Can 3 go into 1? No, it cannot. So we're going to put a 0 there. Now we're going to think about what we talked about with invisible decimal. So 35, we put the decimal after it or to the right of it, and then we annexed a 0. And we can do the same thing with 31. 31 and 10 both have decimals to the right of them. We just don't write them because it gets sloppy after a while. If we had to do that every time we wrote a number, imagine what that would look like. It would get confusing. So that's why we don't do it unless we need to. And in this case, we need to. And we're going to annex a 0. We're going to bring that 0 down. And now we have 10. So we're going to say to ourselves, all right, now how many times does 3 go into 10? Well, the closest, and we're going to get that up above that 0 that we annexed, so every digit has a number above it. So 3 times 3 is 9. 10 minus 9 is 1. We can annex another 0. We can bring that down. And now we have 10 again. You starting to see a pattern? 3 times 3 is 9. And subtract, and we get 1. Now, I'm going to give you a rule of thumb. Is this a math rule? No, but it's a rule of thumb. It's a good rule of thumb. So I'm going to annex one more time, a third time. And I'm going to bring that down, and I'm going to make that 10 one last time. Can I see the pattern? Yes. Do I want to make sure that the pattern stays consistent? Yes, I do. That's why I do 3 places after the decimal. And I'll talk about that again in just a second. So 3 times 3 is 9. Subtract. And we bring down the 1. Now we could keep going. But for our own peace of mind, this is not a remainder. This is what we could continue and keep going and going and going and going and going. But we see the pattern and we see that it's going to keep going. So we can tell ourselves at this point to stop. And I'm giving you permission to stop once you have gone 3 places. Okay? Three places to the right of the decimal point. You may stop. For every problem for the rest of the school year. This gives us enough precision that we can get that number as close to exact as possible. Now, if you notice, this keeps going in a pattern, and that has a name, and it's called a repeating. Let's see if I can get this in here. Decimal. And it means exactly what it says. It says that the quotient right, the quotient being the answer, to the right of the decimal point repeats in a pattern. And there's something that shows the reader, because you do the math not just for yourself, but for other people in life. And when you do that, you have to show people that you know that this is going to keep going and going and going and going. It's a pattern. So you're going to put a line above. I like putting it above the second one to show that it's a pattern. You can put it above the first one, but pick one of the 3s, put a line above it, and that is called a repeat bar. And that shows what the pattern is. Okay? So, let me get a dark blue. A repeating decimal. That means that the more precise you're trying to be, the more you can see that pattern, because you're going to keep dividing farther and farther away from the decimal point. Most of the time, scientists, engineers, chemists, dealing with small particles, they're going to have these small numbers, these small pieces and these small parts. For you, you shouldn't need to go more than 3 places. So I'm just going to write some numbers that have repeating patterns to show you that it might look different than this. So you very much could end up with a quotient that when you get right here, you say, oh, there's a 1, so it's going to have different numbers. And yes, it might. And then the pattern starts to show up when you get to the 3rd digit to the right of the decimal. It is a repeating 3 from this point on. That happens in some problems. There are some problems that come out where the quotient has a 4 and then a 2, and you say, okay, well, we're going to have a bunch of different numbers, and then another 4 shows up. You might want to go to another spot, another place past the decimal point, and you would find that the 4 and the 2 are the repeating. It would go 4 2 4 2 4 2 4 2 forever and ever and ever. So your repeat bar would go over the 4 and the 2. Now there are some numbers that don't have a pattern and can continue to be divided smaller and smaller and smaller and smaller. That doesn't really have a name for it, but my rule of thumb, right? We're going to call this a rule of thumb. It's an old expression. I probably should look it up and figure out where it comes from, but I don't know. We're just going to call it the rule of thumb. So the little rule of thumb that we're going to use is that once you've gone 3 places for most problems to the right of the decimal, you've gone far enough for me. When you get older, you may want to talk to whoever your math teacher is and ask them how far they want you to go. But for me, 3 places to the right of the decimal point. 1, 2, 3. And regardless of what these numbers end up being, they could have a pattern like these do, or they could not have a pattern. You still go 3 spots. And that's far enough for me. All right, so I'm going to back this up one last little bit. I will put a still picture of this in the notes as well as this video.